I think we will start now. Professor Matsagar, can we start now?
Yeah, I think we should
Unmute.
start now. It is 4 minutes
Okay.
past 11.
Okay. So let us start. Hello and welcome to today's webinar. My name is Alok Bhaumik and I am the President of Indian Association of Structural Engineers. Today's webinar is on the theme of advanced base isolation system in real life projects in India. The webinar will be actually conducted in two sessions. This is the first session, and the topic for the first session, as you can see, is fiber reinforced elastomeric isolation system, an indigenous invention for safer future. We are very privileged to have the inventor of this technology as speakers in this session, namely Professor Sajol Kanti Dev and Professor Anjan Datto from IIT Guwahati. The session will be moderated by a very dynamic and young professor from IIT Delhi, Professor Vasant Matsagar, who has been involved in the design of real-life base isolation projects in India, 3 out of which are completed or nearing completion, and 2 are presently under construction. And I thank the speakers and the moderators for agreeing to share their knowledge and experience in this platform. The second session, which is going to be there in the evening, in the afternoon, 3 p.m. onwards, that will be on the topic of new generation sliding base isolation system for improved seismic performance of structures. And for that session, we have Professor R.S. Jangid from IIT Bombay and Professor Vasant Matsagar of IIT Delhi as speakers. Both the speakers have done pioneering research in the field of base isolation, and that session will be moderated by Mr. Vipul Ahuja, who is the Vice President of IS Structi and a well-known expert structural consultant working in the area of base isolated buildings. I sincerely thank the speakers and the moderators of that session too for sharing their knowledge and experience with us today. This webinar is being organized by 2 associations, professional associations, namely Indian Association of Structural Engineers and the Indian Society of Earthquake Technology. Both these associations have many common aims and objectives. IACT provides the forum for scientists and engineers to come together and exchange ideas on the problems of earthquake technology. The association also helps to disseminate knowledge and seismological and engineering aspects and to promote research and development work in the field of earthquake engineering. The Indian Association of Structural Engineers, of which I am the president, is the national apex body of structural engineers in India. This was established in the year 2002 by our legendary Mr. Mahendra Raj ji, and with the objective to cater to the overall professional needs of structural engineers. The association promotes the interest of structural engineering in the country and works towards enhancing their status in civil society. The association aids skill development through various training programs, and this is conducting webinars. CPD, IPD is a very much an integral part of IS Structi activities. Now, let me give a little brief on the reason why we are, having this topic for the webinar today. Earthquake engineering has, as we all know, progressed significantly over the last 6 decades. We had our first code in 1941 of railways, and the Indian Roads Congress had their first code in 1958, way back in 58. In the beginning, the earthquake design used to be very simple, a seismic coefficient method, where we used to simply take a fraction of the vertical load as horizontal load and Nothing else was considered in the design. But from there, the codes have improved in leaps and bounds. Codes have included to begin with, the soil variation factors, the importance factor. Then came the concept of, the flexibility and the stiffness. Then the concept of inelastic design, redundancy, and then thereafter the capacity design principle came into the codes. We are slowly moving towards the performance-based design concept for tall buildings. A new trend for earthquake-resistant design of structure is base isolation, where the structural response is decoupled from the ground motion. And this is a kind of leapfrog jump in terms of seismic safety. There are many structures which should be considered to be operational post a major earthquake, like, for example, hospitals, school buildings, administrative buildings, and some bridges, which are likely to form an important link uh, in the post-disaster, management, relief operations. And base isolation is a solution in such cases. Another trend which is slowly gaining popularity is the use of supplementary damping device in structures which absorbs a portion of the seismic energy. And maybe we will have a separate webinar on that topic. Today, we will be focusing only on base isolation. Now, though in terms of the codes and standards in India, though we have progressed quite a bit in last 50, 60 years, but the fact is the pace of growth is rather slow. In fact, in earthquake engineering, you can divide the countries in two distinct sets. One set of country have significantly reduced their earthquake risk vis-a-vis, the number of deaths. Uh, for example, countries like Japan, USA, New Zealand, they have improved their seismic codes and standards and the earthquake resistant design practice and the construction practices significantly. The other set of countries like India, Pakistan, China, Iran, etc., they continue to cause huge number of deaths in case of earthquake. And there is a wide gap between these two set of countries in respect of the codes and standards and the construction practices as far as the earthquake is concerned. Professional associations like Indian Association of Structural Engineers and the Indian Society of Earthquake Technology, they worked towards reducing this gap between the two set of countries. And this webinar is a step towards that direction to close the gap between the advanced seismically, technologically advanced countries and us. With this backdrop, now let me hand over the floor to Professor Vasant Matsagar to conduct the show. But before I do that, it is my great honor and privilege to introduce Professor Vasant Matsagar, who is the moderator. Professor Matsagar is currently serving as professor and Dogra chair in structural engineering in the Department of Civil Engineering, IIT Delhi. He obtained his doctorate degree from IIT Bombay in 2005 in the area of earthquake engineering for his PhD thesis, which is titled Earthquake Behavior and Impact Response Control of Base Isolated Buildings, a topic which is very relevant to today's webinar. Under the supervision of Professor Jangid, who is also one of the speakers today in the second session, and from which they have been honored with the IIT Bombay Research Paper Award in 2014. In 2014, his patent titled Base Isolation Device for Earthquake Resistant Structures has been awarded, and another patent which is titled Tunable Shock Absorbing Passive Control Device for Vibration and Shock Response Control of Structure has been filed in 2019. So you can see that Professor Vasant Matsagar is very active in the field of this base isolation and earthquake resistant design structures. Also, he has filed a copyright for a method of semi-active vibration control of structures in 2020. He is the recipient of numerous national and international recognition, including Humboldt Research Fellowship for Experienced Researchers, Erasmus Mundus Awards, then DST and DAE Young Scientist Awards, DAAD Research Ambassador and DAAD Awards, IBC Award for Excellence in Built Environment, IEI Young Engineer Award, IIT Delhi Teaching Excellence Award, etc. So he is a person with many feathers in his cap. Professor Matsagar has served as member of the National Building Code, NBC 2016 of India, and is currently serving on Code Development Committee in the Bureau of Indian Standards, in Indian Roads Congress, and International Standard Organization, ISO. In BIS, he is currently serving as member of the Earthquake Engineering Sectional Committee, that is CED 39, for Indian Standards Code IS 1893. In ISO, he is currently serving as the working group member on seismically isolated structures. Currently, Professor Matsagar is also serving as editor-in-chief of IACT Journal and convener of the Structural Dynamics Forum of the IACT. He is an editorial board member of the Bulletin of New Zealand Society for Earthquake Engineering, Proceedings of the Institution of Civil Engineers, Structures and Buildings, Advances in Civil Engineering, Indian Concrete Journal, ICJ, and few others. He is guest editor of journals, namely Institution of Engineers India Series A, Shock and Vibration Frontiers in Built Environment, Journal of Low Frequency Noise, Vibration and Active Control, and he has served as responsible editor of the Earthquake Spectra Journal. As I mentioned earlier, Professor Matsagar has been involved in the designs of 5 real-life base isolation projects in India, 3 out of which are completed and 2 are presently under construction. Today, he will be one of the speaker also in the session number 2 in this, at 3 p.m. This next session. So I now hand over this floor to Professor Matsagar to conduct the show. Thank you very much.
Okay, thank you so much, Bhavamik sir, for the nice words of introduction. I really appreciate it. Good morning, one and all. Straight away to go ahead with our technical session. It is my indeed pleasure to introduce our first speaker for today, Professor Sajal Kanti Dev from IIT Guwahati. So Professor Dev has obtained his PhD degree from University of Roorkee in the area of earthquake engineering in 1994. He is presently working as Professor of Civil Engineering, and he is also the Dean Resource Generation and Finance in IIT Guwahati. His area of research interest include earthquake resistant design, passive control, structural health monitoring, seismic retrofitting, hybrid fiber reinforced concrete, and active confinement of reinforced concrete bridge piers. He has guided 9 PhD research scholars thus far, and there are 5 more research scholars working for their doctoral research under his supervision. He has guided more than 50 master's students for their master's thesis and published more than 40 papers in reputed national and international journals. The total number of publications in the refereed journals and conferences are in the range of 80 or higher. He has authored a chapter in the handbook titled Seismic Retrofit of Buildings, developed under the joint initiative of Central Public Works Department and IIT Madras, which was published in India by Narosa Publication. He has also served as principal investigator and co-principal investigator in 12 research and development projects related to structural and earthquake engineering sponsored by different funding agencies. He was also project investigator of an international project sponsored by Royal Society UK, which was a part of collaborative research with Durham University in UK. Professor Dev has coordinated development of state-of-the-art dynamics testing facility, earthquake simulator test facility, and hybrid simulation facility at IIT Guwahati during the initial stages. He has delivered and currently engaged in many important and challenging consultancy works to various organizations such as Kolkata Metro, NF Railway, Southeastern Railway, Eastern Railway, and so on. He was the principal investigator of a team that developed efficient and cost-effective base isolation systems, which is the topic of today's presentation. And the project was named Fiber Reinforced Elastomeric Isolators, which is used for seismic isolation of two-story stone masonry building in Arunachal Pradesh. He has been bestowed upon with numerous awards. Some of the selected honors that Professor S.K. Dev has received includes Professor A.S. Arya IIT Roorkee Research Award in the year 2016 on disaster prevention during annual convocation of the institute. He has also received Dr. Jay Krishna Medal in the 17th Engineering Congress organized by Institution of Engineers India in 2001. Professor Dev has served as a member in many editorial panels, expert committees. He has delivered a number of invited lectures in institutions of international and national importance, including ELSA, ISPRA, Italy, Saitama University in Japan, NSRI in Taipei, Durham University in UK, several IITs and ISC, Bhabha Atomic Research Center, Jadavpur University, and so on. So with this, I would request Professor Dev to deliver his first talk in the session 1 on fiber reinforced elastomeric isolation system and indigenous invention for safer future. Meanwhile, I will also request all the attendees and the participants of this webinar to put their questions in the chat box. I request Professor Dev to take over, please.
Thank you, Professor Matsragar. I hope you can hear me.
Yes, you are audible, sir.
Okay. For a nice introduction and very good morning to all the participants. At the outset, I would like to thank Indian Association of Structural Engineers, ISET, for providing me this platform to interact with the participants. Particularly, I am thankful to Engineer Bhomik. He come up with this suggestion for this particular webinar. Well, I shall be talking today, as already notified, on fiber reinforced elastomeric isolator, which we call it FREI, and we are involved in research work on this particular system since 2009. Okay, we have initiated this research on this, and although I mean this research have been initiated by Professor none other than Professor Kelly, who happened to be a pioneer in the field of seismic base isolation, and he first, I mean, I could find a first paper published by him in 2001 or so, around 2000. So in this area, I mean, 2 of our PhD students completed their, I mean, work, and a couple of master student and 1 BTech student also contributed. So what I'm going to present is the work of all members of this particular group, including these 2 PhD students. Okay. So to start with, I shall talk a little bit about, I mean, concept of base isolation, because I understand many students will be present over here, and they may not be, I mean, conversant with the concept of base isolation. So around 10 minutes I shall spend on that, and remaining time, you know, I shall be devoting on topic of today's presentation. Okay, so these are the, I mean, a member of the research group.
Sir, kindly share your screen.
I have shared.
It is not yet visible, at least at my end.
No, we can't see.
Okay, what is the problem?
There is a green button below. Professor.
Yeah, then I'm going out again.
No, you have you pressed the green button?
Green button I could not see.
If you see at the bottom, there is a green button which says share screen.
Now, that I have done before, and they could see earlier.
इधर जाओ
যেতে বাইরে এখানে মিনিমাইজ
তুমি তো জুমে নাই
না জুমে না থাকলে শুনবো কিরকম এটা তো ওয়েবসাইটে
এটা কি তো কোথায় গেল এটা এই যে এখানে শেয়ার করতে
ওকে
Yeah, now it is coming.
Yeah, it is
Okay, okay.
visible now. Thank you.
So
Yeah.
So other group members of this research group are Professor Ranjan Datta, who is my colleague, and we are, collaborating with each other since, 2000. Of course, he will be talking about, the same topic, other issues, like your finite element analysis, stability analysis in the second lecture of this particular session. This is Dr. Tuet. He was one of the research scholar with whom we have developed the, this prototype of the FREI, and he's from actually University of Hanoi. He completed his PhD in 2017. Dr. Onimesh Das, first PhD student in the topic. Currently, he is associated with the BHL New Delhi. Then Mr. Hajarika, who was with us, our former PhD student, Reddy, undergraduate student. I also like to acknowledge the help of Mr. Bishwajit Devnath, who helped us in your experimental endeavor, and our industry partner who fabricated this bearing for us, Metco Private Limited, Kolkata. Now, outline of the presentation is something like this. Initially, quickly, I shall talk about basic issues, limitation of conventional design, conventional earthquake-resistant design, to be more precise, different component of structural control, basic concept of the base isolation, design issues, and then we shall start main theme of this today's presentation, that is FREIs. I shall talk about bonded isolation, what is the how they are different from unbonded isolated and unbonded FREIs, horizontal force displacement hysteric behavior of UFREI. Particularly, we shall be concentrating on UFREI, unbonded fiber reinforced elastomeric isolator. That is what we have implemented. Okay, and its performance are superior to bonded FREIs. So our main focus will be on UFREI. There, horizontal force displacement hysteric behavior I shall highlight. Thereafter, first we shall confine our discussion on model UFREI. Then shake table testing we have carried out for isolating a unreinforced masonry test model using that model bearing. Then we shall go for discussion on prototype FREIs, or more precisely UFREIs. Then using the same prototype, we have constructed one building in Arunachal Pradesh. And what is the extent of reduction of seismic vulnerabilities? A couple of slides I shall discuss over here. And then we have initiated research work on partially bonded FREIs, which is improvement on which take advantage of both bonded and unbonded FREIs. Just we have initiated this work, and January we expect to start experimental work. So I shall highlight to some extent this partially bonded isolator. So this will be the content of today's presentation. Now, all of us know what is the problem with conventional earthquake resistant design philosophy. Now we rely on damage in the structure in certain specified location, for enhancing your enhancing ductility in the overall system. So that means what? We are ensuring safety by deliberately allowing damage in certain location, pre-decided location in this structure. So structure cannot be realistically designed in elastic manner. Okay. particularly in region of high seismicity. Now, common practice is to design them so that they experiences damage in a controlled manner. That is what I told you, and this they undergo large inelastic excursion, and thereby we get this, uh, earthquake resistance because of your ductility, which allows, redistribution of, stress resultants. So this is what we want to avoid. We want to avoid or minimize to a large extent the damage in the structure. So what are the options? Conventional structure cannot avoid that. Even if you follow the codal provision, there will be damage, maybe in controlled manner. So that is what if you want to avoid. And another thing, conventional structure actually ensures life safety performance level. So if you want to design a structure for higher performance level, then you'll have to go for structural control techniques. Okay. So there are, three types of your structural control techniques. One is your enhancing damping to dissipate seismic energy coming into the structure. Another is isolating the structure from the ground. Okay, so the base isolation comes under this category. We shall concentrating on this basically today. Okay, there are other way of doing it. In some flexible structure, you may have to require, may have to stiffen the structure. So these are the different component of your structural control. So basically, we can divide, or classify the structural control in three classes: active system, passive system, hybrid system. You see, if you focus your attention over here, which base isolation, you see, is under passive system. So passive system are those which are activated by the structural motion during earthquake. Okay, so we don't need any, actuation force or power supply for this class of your passive system, and probably our country is ready for this kind of your systems for high performance seismic design. In active system, you need controller, you need actuators, you need power supply, so and these are expensive. Okay, and during earthquake you need power supply. Okay, so expecting that in our country is a bit too much. Okay, now to some extent, complexities or demand, on actuators and controllers, etc., are minimized in hybrid system. Okay, so these are combination of passive system and active system, but I'm not discussing this to save time. Our main focus will be on base isolation. Although we are doing some work on work on your seismic, energy dissipation, or energy dissipation device. We have developed already. Some energy dissipation device prototype we are developing. Model we have already developed, and a couple of our PhD students working in this area. So maybe in some other occasion we may talk about that. Today, basically, our main focus will be on seismic isolation. First, I shall talk about, as I told you already, basic principle. It will be applicable for both conventional isolator, that is steel reinforced elastomeric isolator, as well as fiber reinforced elastomeric isolator. Okay, so here, you can see that this slide you might have seen on many occasions. This is a, structure which is supported by, isolators. It may be steel reinforced conventional base isolator or fiber reinforced isolator, and this is conventional structure. Here you can see, although this plot is, little bit of exaggeration, but still you can see, if you compare this structure here, interstory drift will be higher, and damage is, direct, linkage or proportional to your interstory drift. Higher the interstory drift, damage in the structure will be more. But here you can see interstory drift is very, very small. More or less, this structure will be behaving as a rigid body, and all the deformation will be concentrated in the, isolation system. This is the discrete isolation system. Generally, we provide under the columns. Now, this isolation system, if it is bonded, they will be deforming in this pattern. In shear deformation will be there. Okay, so this is how it is going to deform. Okay, but unbonded isolation system, what we are, will be the main focus of this presentation will be deformed shape will be a little bit different from this. So conventional isolator or bonded FREI, that is fiber reinforced isolator, will be deforming in this particular fashion. Now, once you mount your building on isolators, basically what it does, it decouples the building from the damaging component of your earthquake input motion. Okay, and thus prevent the superstructure of the building from absorbing earthquake energy. Entire superstructure must be supported on discrete isolators whose dynamic characteristics are chosen to uncouple the uh, ground motion. Okay, so here comes the role of design of this isolator. Okay, how to fix the dynamic characteristics of these isolators, so that we can decouple and there is no transmissibility of ground motion to the superstructure will be minimized. So that is what we are going to discuss today. Now, before I discuss that, all the particular PCIP system has their limitations, so we should know, under what circumstance they will be effective. Okay, so here are certain 4 points I have noted. Under this, limitation you will have to work. So base isolation will be less effective, if subsoil is experiencing your predominance of long period ground motion. Okay. So we'll have to ensure that subsoil does not produce, a predominance of the long period ground motion. Not that we cannot design, we can design, but displacement demand on the isolator will be very, very high. So we'll have to design that. Building aspect ratio should be about 2 to 2.5 for high effectiveness of the seismic isolation system, and columns load should be sufficiently high. Okay. So these are the two main limitations. Then the site should permit horizontal accommodation of your horizontal displacement at the base of the superstructure, and that is of the order of say 200 to 300 millimeter, or some cases it may be more, if this condition is not adhered to. And then this isolation system will experience other kind of vibration also, maybe because of ambient sources or wind. So we'll have to ensure that lateral load due to wind are generally less than around 10% of the weight of the structure. So if we fulfill this limitation, this isolator will be highly effective. Now this slide will give you an idea. Many of you know already, but this is specifically for students, how this isolation system helps, how it reduces the transmissibility. Now if you just ensure this building aspect ratio, this aspect ratio means height to width, least lateral dimension. This is what is one geometrical parameter. This is what we call it aspect ratio in this zone. Time period of the building. Okay, this is a idealized response spectrum. I hope all of you are aware, particular student, I'm referring to the students, aware of seismic acceleration response spectrum, pseudo acceleration response spectrum to be more precise. It is a plot of your time period in the x-axis and spectral acceleration or maximum acceleration in simple term, in the y-axis. Okay, so you see here, if in this time period, which is function of your stiffness and mass and their distribution along the height, so there may be multiple, time periods in a structure. Particularly structures are all multi-degree freedom system. But if it is a base solid structure, it is something like this. If it is, we consider this is a rigid body, which is not incorrect. Okay, in that case, we can, idealize this as a single degree freedom system, and in that case, it will have, single time period, and if its time period is of the, your this thing, conventional structure in this zone, say fundamental period in this zone, where amplification is very high. Now, once you incorporate flexibility by placing the isolator at the interface of the superstructure and substructure, flexibility in horizontal direction will be imposed, and then that will shift the time period in a zone around this, and in that case, you see amplification will reduce from green dot is coming down to red dot, and here this you see spectral acceleration is very, very less, so that's how we ensure that ensure low transmissibility by shifting this time period, or in other words, physically by providing flexibility at the interface, flexibility particularly in horizontal direction. Okay, thereby we ensure, low transmissibility. And in addition, if we can increase the damping, nothing like it, this, you see, red dot will come down further. This top curve is for a response spectrum for low damping, bottom one is for higher damping. So if you increase damping, further your spectral acceleration will be reducing. And this increase in damping is also important from another, perspective. We are looking here, transmissibility of acceleration. What about displacement? Now, displacement will be significant at the base. So if you want to reduce or you want to keep it in control, your damping also play a huge role. So this damping will reduce the displacement that will be imposed on the isolator, base isolator. Okay. So this is the basic principle how we reduce the transmissibility. Okay. Now, as I told you here, what is the target time period here? Target time period of the base isolated system is generally around 2 seconds or 0.5 hertz. Okay. So that is what at this, base displacement is controllable. At the same time, transmissibility of the acceleration also, reduced to a large extent. So this is the optimum value. If you remember, this will be around 2 seconds or which corresponds to 0.5 hertz for the base isolated building. Okay. So if we consider, now I'm talking about how we can design, just preliminary guideline how we can design this isolator. So this will be around, say, as I told you, 2 seconds or 0.5 hertz. Total mass, which includes seismic weight also here, that we can determine. And once we know that from this simple, equation for, frequency, we can find out what is the total horizontal stiffness we need for achieving that particular, frequency. All right. So then you divide that cage, capital cage, divided by number of bearings. So what is the, stiffness of one bearing, that you need to provide, So whether it is SREI or this is applicable for bonded FREI also, you can relate, geometrical property of this isolator, say material property of the isolators, G is the rubber, shear modulus of the rubber. This is the area of your bearing. This is the total rubber thickness. So if we assume the area, you can find the total rubber thickness for a given, G value or shear modulus of the rubber. And if you fix, they say TR, you can find what is the A. So thus we can proportion the, isolator from, this simple equation. Okay, this is of course developed for SREI. Now, what we have done here in this particular, as I told you, we have carried out a study for around 10 long years. We have proposed an equation for FREI for this, that I am going to discuss later. Okay, so earlier we used to, proportion using this one. And as I told you, this should be, idealized force displacement behavior of the seismic isolation system. Initial stiffness should be high. And then once you cross certain threshold value, okay, in terms of force or in terms of displacement, stiffness should drop. Now, why, we are providing high initial stiffness? Because as I told you, we have to take care of that, this ambient, forces, whether it is because of wind or other sources, so that if you want to control, we cannot allow, we have designed the system for earthquake safety, but it should not cause problem, for during, when building, it will be experiencing this ambient vibration. So high stiffness, but in case of your moderate high, seismic event, this threshold will be crossed and stiffness will drop, and again, once you withdraw that load, it will be, load will be reversing. And then again, if you apply load, high intensity load in the, negative direction, this will be the, load displacement behavior. So if we apply a cyclic load in a cyclic displacement, to be more precise, in a bearing, this will be the, I mean, load displacement characteristics. So this is a typical idealized characteristic. So this is what we aim for, isn't it? So that we can avoid unwanted vibration. At the same time, we can reduce the stiffness for, I mean, achieving this frequency of 0.5 hertz in the isolated structure, or 2 seconds of the time period. Okay, so this is the objective. This is what we do. Now, how we achieve, I mean, this your low stiffness in horizontal direction, but at the same time, this same unit has to transfer our column load, so they should have sufficient vertical, I mean, stiffness, and in turn they provide vertical stability, is that it? So how we achieve that? We divide whatever you say. Suppose we fix certain G value, say this is generally around, say, 0.6 to 0.9 MPa generally we fix. Okay, and this area you can fix. Then you can find the total rubber thickness. Now, rubber thickness, if you provide in one, I mean, layer, then there will be bulging, so there will be bulging. So to prevent that bulging, or in other words, the bulging means what? Vertical stiffness is very low. So enhance the vertical stiffness. What we do, we provide layers, alternate layers of steel, and originally we wish to provide conventional laminated rubber bearing. We wish to provide, steel layer and alternate layer your elastomer or natural rubber, isn't it? So instead of providing in one layer this total tier, we provide in multiple layer, and thereby what we do, we enhance the, I mean, vertical stiffness. How vertical stiffness is enhanced? Because bulging will be restricted. So what is the role of the steel plate? I mean, what we provide here is a section. You can see here steel plates. The black lines are steel plates. What is the role of steel plates? Basically, they does only one thing. They prevent the bulging. That's it. Okay. So once we prevent the bulging, that means, I mean, vertical stiffness will increase enormously. If we provide multiple rubber layers, with, I mean, intermediate, steel layers, then vertical stiffness will increase, and also that will give you high vertical stability, isn't it? And rocking mode of vibration and all will be avoided. So this is how, this is the basic, I mean, principle of your laminated rubber bearings or elastomeric rubber bearings. Okay. So now, how, if it is a bonded, so in bonded isolated, generally there will be a end plates at the top and bottom of the isolators, and these are how they are connected, with anchor bolts, with the superstructure above and substructure below. Okay, so these are also not easy tasks. These are difficult tasks. Okay, so if we want, I mean, widespread application of seismic base isolation, we'll have to enhance the ease of your installation. Okay, and this, once you reinforce with the steel plates, the weight of these isolators are quite heavy. Okay, weight of the isolators are quite heavy. Okay, so that we, if we want to reduce, then we'll have to think of some other material. That's how, FREI come into the picture. FREI, FREI, I mean, in basically reinforcement material is what? Carbon fiber fabrics. Okay, carbon fiber fabrics, they replace the steel plate. So there will be substantial, I mean, reduction in the weight of the isolators. Okay, but they are equally or even more efficient in preventing the bulge, because E value of the your fiber, much higher compared to steel. So that's how, so we are, I mean, just in FREI, we replace this steel plate reinforcement by your fiber fabric reinforcement. Okay, in both the direction we provide this is, I mean, reinforcement. So that thereby, I mean, we reduce the weight, and also in unbonded case, this anchor, I mean, are not required. Anchor bolts are not required. So that also, I mean, increase the ease of installation. Okay. Now, as I told you, two things, I know, as I already told you or shown you in this slide, this elements will be subjected to large deformation. Okay, and this superstructure will be experiencing very low, I mean, interstory drift. So this element should be, I mean, should be able to, I mean, carry both your high vertical load transferred from the column, as well as this large horizontal deformation this will be experiencing. Both these two actions it has to take into account, So estimation of what is the maximum displacement, maximum displacement is very important. Okay, so there are many codes, this thing here I have referred AC7, 2016 version, and here you will find how to find out what is the maximum displacement that will be experienced by the isolators. Okay, so this is DM actually, as per their US hazard estimation there is probabilistic in nature. So they defined maximum credible earthquake, that means maximum earthquake. Okay, uh, and under 5% damping, spectral acceleration corresponding to 1 second, we shall use here, you see, SM1, 1 second period. Okay, this TM is what? TM is not, this is not, this is TM, this is not TM1, this is a mistake. This is effective period. Okay, what is the effective period? Okay, as I already told you that we need, bilinear behavior, idealized bilinear, initial high stiffness followed by low stiffness, once you cross a threshold. So this is your force displacement hysteresis loop, So this is for a particular one displacement amplitude. This one side, displacement amplitude, you are getting this particular figure. Now this dashed line shows your effective stiffness. So this effective stiffness is used for finding out your this TM. Okay, so that TM we'll have to put it over here. Okay, and this BM corresponds to damping. Okay, this BM is a function of damping, and you can find this from any code like AC or other code. So how to find out, this BM, this depends on what is the damping. Okay, now this TM, how can be calculated? What simple equation, because base isolated building act as a, basically a single degree freedom system. So you can use this particular equation to find out TM. What is this KM? KM is your effective stiffness. So this KM is nothing but this gradient of this line, dashed line. Okay. So once you know KM, once you know, seismic weight of the structure, you can find out TM. Once you find TM, and once you find SM from your spectrum, spectrum, and this corresponds to 1 second time period, So, and BM, as I told you, is a function of damping. You can estimate what is the DM. Roughly, this is what the procedure finding out DM. Okay. So these isolators, whether it is elastomeric, fiber reinforced elastomeric isolator or steel reinforced elastomeric isolator or any other isolator, has to, ensure that, they can take the vertical load and simultaneous action of your vertical load from column and also impose displacement of this order. Okay, so this is what you'll have to ensure in the design. How to find out? The DM is basically at the center of resistance. Now at any point, any other point, there will be some eccentricity, and how to find out your in other locations, in column location or isolated location, that you can find once you find the DM. This is not DD, this is DM actually. Once you find this in various location, in the building footprint, there will be isolators, and how to find out what will be the displacement, that you can find out from this equation as given in this. I'm not going in detail. And this total displacement, okay, DTM, this one should be, should not be taken less than 1.15 times the DM. Okay, so if it is less than 1.15 times DM, then you will have to consider at least 1.15 times DM. That is 15% more corresponding to this DM. So these are the two things you will have to consider in isolated design. These are very important things. Okay. So now this is what is first isolated building, what most probably in our country also, it's constructed in 2004. Okay. And this is on your steel reinforced elastomeric isolator. Okay. We have designed this isolator, but we got it manufactured from somewhere else. Our sponsor supplied, our sponsor was your BRNS. This is a R&D project. So BRNS, Department of Energy, they have supplied this as per our design. And this is, you see installation process. I can show you this isolator, which is having around 50-ton capacity, was weighing around 400, kg. Okay, so it is not light, and you will have to ensure that all the anchors are in place. So template is required. So things are not that easy. So that we that time we have decided, can we explore, some ways and means for reducing the weight and increase the age of installation. Okay, so that is how we started, work on, your fiber reinforced elastomeric isolator. Okay, so we have, recorded ground motion during actual earthquake of this particular building. This is, base isolated, and exactly, same replica of this superstructure is here. This is non-isolated or conventional, and then we compared the response of both the structure, and we found that base isolation is very effective in controlling the seismic response. So this is the experimental building. Still, it is there. Okay, in our IT campus, IT Guwahati campus. Okay, so base isolation is effective undoubtedly, and here you see extent of reduction is 76%, maximum and minimum is 20% reduction. Normal building, it will be amplification. No, conventional building acts as an amplifier. Here, no question of amplification, reduction. It may appear 20% is insignificant. No, it is significant, because if you compare with the amplified, response of the conventional building with this, it is substantial reduction in transmissibility. Okay, so base isolation is effective without doubt. Then, as I told you, because of those limitation, high weight, and to reduce the complexity, we started thinking differently. So at that point of time, we came across this publication from Professor Kelly around 99. As I told you, this was first published work in FREI, that is fiber reinforced elastomeric isolator. And then we also started around 2009, 2010, and we also published around seven papers already in top international journals. So I'm not going into details of the review. These are some papers, important papers I have highlighted over here. Recently, 2009, there is a state of art paper, by Van Ingelen. Is one group active in Canada, because not many groups are working in this. Professor Kelly and his group, then one group in McMaster University, and there is a couple of group in Italy, and our group. There are around, say, maximum not more than 10 groups are working in this particular area. So, and in this review paper, he reviewed around 109 or 10 papers, and all our 6-7 papers are included in this particular review. So if you are interested in this, you can collect this particular paper published in Soil Dynamics and Earthquake Engineering, Van Ingelen, and you will get all the papers what are available in this particular area. So to start with, I shall share, what is the difference between load transfer mechanism of bonded FREI, whether it is your steel reinforced isolator or fiber reinforced isolator. If it are bonded with the superstructure at the top and at the bottom with the substructure, this will be, free body diagram. Okay. So here you see, Professor Datta will be talking about your fiber, your finite element analysis. There you can see the stress distribution. And from that stress distribution, you can arrive at this, stress resultant at the top and bottom. And here you see, a large section. If you see you'll see in the second lecture, large portion, particularly this area and this area, corner area, this acute angle corner areas will be subjected to your high tensile stress. Okay. High tensile stress. And you see here, if you compare this point of application of the vertical load is still at the center of the bearing at the top and also at the bottom. But here, if you see, the point of application of the resultant, point of application of the load from the column gets shifted from center when it is in bonded condition for low, excitation level to high excitation. This, point of application shift towards left in the top, and at the bottom towards the right, or it may be vice versa. It depends on your direction of the excitation. So here you see this offset, horizontal offset between these two forces, P and P, reactive force and active force here, that will cause a, I mean, moment, in counterclockwise direction, and that will balance this moment because of this shear at the top and bottom. Here you see, here, I mean, this moment will be coming to the picture, so for equilibrium, but this moment will not be getting mobilized over here in unbonded application. So this is the basic difference between the load transfer mechanics of the unbonded isolator, whether it is your steel reinforced or FREI, bonded FREI, and here it is totally different. Mechanics is totally different. It is unbonded fiber reinforced elastomeric isolator. So this is the point you honest to, I mean, understand at the beginning. Now this is, I mean, model your FREIs, and what are the advantages? Use of fiber reduces the weight that I told you. Some, I mean, modification will be there in manufacturing technologies, sandblasting, acid cleaning, etc. is not required. You can go for long strips, and then you can cut to smaller sizes, but this is very difficult exercise we have seen. We have designed, I mean, FREI, FREI for model FREI to start with. Okay, so model FREI to start with. This is the geometry, this is the elastomer layer. The black line is your fabric, carbon fiber fabric to be more precise. Okay, so we have designed this. We have calculated the, I mean, critical load also, and that critical load should be much higher compared to the vertical load. Okay, so maybe around, say, around 100 times or 200 times than your vertical load. So that you can avoid those unwanted mode of vibration like rocking mode of vibrations. Okay, but it allow horizontal flexibility to reduce the transmissibility of the excitations in the horizontal directions. So once we design that, we have, I mean, these are, I mean, schematic diagram. These are the bearings. We have applied load with whatever, I mean, concrete slabs and test model we have in our lab, and we applied with the horizontal actuators. Okay, so it is subjected to vertical load. What we expect, in shapable test model will impose on these 4 isolators, and we applied the, I mean, horizontal displacement, cyclic horizontal displacement using servohydraulic actuators, and this is the deformed shape at the higher displacement. Okay, so it is losing contact, losing contact, or this is what is also known as your rollover deformation. This is displacement is imposed in parallel to these edges. This is along the diagonal to see, I mean, how loading direction impact the parameter like effective horizontal stiffness. Now, if you see effective horizontal stiffness, already I have defined over here. This is effective horizontal stiffness. Once you get this force displacement hysteresis loop from the experiment, you can find this for a, and this effective horizontal stiffness will be different for different amplitude. With higher amplitude, this will drop. Okay, so this is what we expect. So if you see over here, first for this one, second for this one, initially for low, I mean, displacement, this is 10 mm displacement, this is corresponding to 50 mm displacement, if I recall correctly, stiffness is dropping. So that is what we want, higher stiffness is the low displacement level. Okay, that will ensure that those unwanted mode of vibration because of wind and all will not be exciting the structure. So with the, I mean, increase in the damping, displacement, your stiffness is dropping, and thereby it is enhancing the, I mean, effectiveness of the damping by reducing the transmissibility. And also you can see here, damping is increasing. Now you may wonder how our work is different from what have been reported in literature, but whether it is, I mean, from work by Tate and others, work carried out in McMaster University or Professor Kelly's work, if you see damping, they didn't get the increase in damping. Okay, the damping reduced with the I mean, displacement. Now in our case, damping is increasing with the displacement. So that is the one fine attribute of our this thing. And manufacturing technology, our manufacturing technology is different from theirs. They used cold vulcanization. We used hot vulcanization technique. Okay, so this is very challenging task to vulcanize steel, and elastomer is well understood, but with the help of our industry partner, we developed the technology for vulcanization, hot vulcanization of your elastomer and your fiber fabric. So this is what is our innovation is all about, you know. So higher damping with a higher displacement level, that is one addition, and that vulcanization process. So this is what is the main outcome of our innovation. This is the uh, a typical hysteresis loop at 50 mm, 60 mm. There are many more loops, and here this dotted line is test result we got from experiments, as I have shown the experimental setup, and also we have simulated these loops. So Professor Datta will talk about how we have simulated this force displacement hysteretic behavior using finite element analysis in the second presentation. Okay. So this work got published in one of the reputed journals, the Structural Control and Health Monitoring, in 2015. And after that, you know, these again, you see, these are for model bearing. Okay, these are model elastomeric bearing. With these are model elastomeric bearing, and plane area is 100 mm by 100 mm, and height is also 100 mm roughly. So this is for whatever I have shown. This is for model bearing. So with this model bearing, you know, horizontal force displacement behavior, once we ensured satisfactory behavior, we gone for earthquake simulator testing. A small shake table what we have in our lab in IIT Guwahati, we use that, and this is a unreinforced masonry building, you know, and this is subjected to ground motion using rather simulated ground motion using this shake table, and we measured acceleration response along the height. Also we measured the displacement with respect to table, you know, at these two levels using LVDT. And this work also got published in Earthquake Engineering Structural Dynamics in the year 2016. Okay, so this is the excitations. We have used 4 excitation with 4 different set of characteristics. So this is Koina earthquake, and you see is more than 0.63 G. So this excitation is quite high excitation, and then part field excitation is 0.45 or something like that. Is peak acceleration. This is around 0.35 for El Centro, and similarly for Mexico City earthquake. And this is, deform, shape or rollover deformation or loss of contact you can see during seismic simulator, earthquake simulator testing or shake table testing. And entire system was stable in spite of losing contact here at the top and bottom, you know, there is no problem as such. So here, this is for part field earthquake, this 0.45, if I recall correctly, is the peak ground acceleration. This is quite high. And in Koina also, it is 0.63. Okay, so this is the deformed shape during shake table excitations. I have the this thing video also, but I have not, because of this video presentation, I have not shown that. There will be a lot of problem. Now here you see, this is the table, light response history shows your table motion, and the deep one shows that for at the base level here. Okay, base level for Koina, and you see a lot of reduction of the in transmissibility of ground motion, you know. In fixed base, this will be, as you move towards the top, you know, it will increase, it will amplify. Here it is getting reduced. Okay, so isolator what we have designed is effective in all, irrespective of characteristics of the ground motion. It is reduction anyway. Okay, and here at the base level, first floor level and roof level, what are the acceleration we have plotted, and you see more or less they are overlapping on the one another. That means what? There is no amplification of acceleration as we are moving from this bottom accelerometer to the top accelerometer. There is not much amplification. So basically, this body, this test model of unreinforced masonry is basically acting as a rigid body. Okay, and there is very low, low interstory drift, and that is evident from this figure. Here we have shown displacement time history, displacement at the base level and first floor level both are overlapping over the one another, isn't it? So there is no negligibly small interstory drift. Okay, so this show that our isolation design is okay. Okay, and it is very effective. All right, now here you can see what is the peak acceleration, peak table acceleration 0.63 g, and at the base what we experienced roughly 1/8 of that. Okay, roughly 1/8 of that or 1/7 of that. Okay, so large reduction in Koina. In Parkfield earthquake, around say 60% reduction at the base level. In El Centro, around say 50% reduction. So this reduction is function of characteristic of ground motion. So this is what we see in passive control. In active control devices, more or less their effectiveness will be, more or less same, because we shall be tuning their property in real time, but in passive system we cannot do that. So their effectiveness will vary with the ground motion characteristics, and that is what is reflected over here. But nevertheless, in all cases, we got a reduction more than your 50%. Okay, so our base isolation system is very effective. So this is the based on this model study. After that, we gone for we thought of implementing this in one prototype building. Okay, so this is a prototype bearing we have designed for one building. I shall show you in subsequent slide. So there are two sets of bearing we have designed. One is about 35 ton caps. Pardon?
Yeah, so you can expedite to go to.
Okay.
Yeah, thank you.
So this is around how much time I have around?
Actually, we started a little late, so still
another 10-15 minutes. Okay, I shall try to conclude. Huh?
Okay, thank you.
Okay, so this is a prototype building, a prototype bearing FREI, unbonded FREI to be more precise. This is highest capacity was 55 ton, and second category was having 35 ton capacity. And earlier, as I told you, the steel reinforced isolators, elastomeric isolator, what we used in our base isolator building, that also having 50 ton capacity, that weighing around 400 kg. This is weighing around 15 kg or so. You can lift with your hand. Okay, and here there is no end plate at the top and bottom. So these are the some this thing, and this also we have tested. This was a makeshift arrangement we have made because we didn't have the idle bearing testing facility at that point of time. Now we are procuring one. Probably this month we shall be installing one hydraulic press specifically for designing, testing your seismic isolator. Okay, up to a 300 ton capacity. Okay, that is also not big, but that is what we can afford. So cyclic displacement we applied with our available actuators, and this vertical load we applied with this CTM or compression testing machine. We have modified a little bit, and vertical pressure is around 0.56 MPa, and this imposed displacement frequency is this. Okay, so time period is around 40 seconds one cycle, and we used up to say 90% of the shear strain we have applied or imposed 90% of shear strain experimental study because of certain limitations in experimental setup. But in final element model we applied up to 170%. Okay, so that is quite high. We tuned our finite element program. That is what Professor Datta will talk about that in the second session. So this is, you can see, during testing, this is losing, this contact, or it is undergoing rollover deformations. These are the, hysteresis loop. 4 types of isolation system we have tested, 4 different types of specimen. And with the increase in displacement, you can see this effective stiffness is getting reduced. Yeah. Initially it is this, and finally it is this gradient is reduced. Okay. So here, as usual, what we have seen in model also, here effective stiffness is getting reduced. Damping is increasing, all 4 I mean, varieties of the bearing, prototype bearing what we have tested. This is how we have found out this effective stiffness and damping. And based on this damping, you can find that beta B factor what we considered while estimation of what is the maximum damping. Okay. So this is, this I shall skip. Professor Datta will talk about it. Simulating the experimental behavior using finite element analysis, and both are matching very nicely. And as I told you, this is what we have done of your this thing, experimental work. This is your numerical result, So if you compare this and this, these are quite good, compare this and this quite good. And this is what Professor Datta will discuss. So I am skipping this. And then this is from this kind of curve, we can get the envelope curve. So envelope curve will be something like this for this, So if you compare the envelope curve of the bonded and unbonded one, bonded one is this blue line and unbonded one is this. So drop in stiffness in unbonded one is much higher, compared to this. And that's why this unbonded, isolators are more effective, okay, in controlling the seismic response. But we are not losing their stability, okay, that we have ensured. Now, this is what is our contribution. As I told you, initially, we found out, stiffness of the isolator from G into A divided by TR. Now, this is for unbonded one. This is what we have proposed. Okay, G we are replacing by G effective. How we get G effective? That is what Professor Datta again will be talking about it. And as because there is a rollover deformation, so area of contact will reduce. How to find out this contact area, that is explained in this particular figure, and this because of loss of contact, how we can find this effective area. This is what is explained over here. Because of paucity of time, I am just moving a little bit fast. Okay, so this can be found. What is the reduction in the area in the unbonded FREI corresponding to a certain displacement? U is the imposed displacement. For that, what will be the reduction in area? We can find out this. Okay. Now, what is this D? D is this projected area of this curve length. This curve length S is equal to nothing but imposed displacement. So how to find out that? That is depend on H, and this alpha is a geometrical parameter which relates this D and S. So this is what we have proposed. Okay. How to find out G effective? What is the basis? As I told you, this will be explained by Professor Datta. And this is the equation we have proposed. One equation we have proposed. And in this, what is the definition of critical load? It is defined here. How we can find critical load? G, that is a shear modulus. This is area, then shape factor. These are all geometric properties. S and A. This R is the radius of gyration, and G is the material property. And this is another, proposed method you'll find in this particular paper published in 2017, again in earthquake engineering and structural dynamics. And this equation actually is earlier equation is for entire displacement range. So here with displacement range, we have split into two, and accordingly we have two equations. So this is better compared to other one, but this is little bit involved compared to our earlier one. So this is another contribution we made. And then implementation, this is the building we have isolated, using our unbonded fiber reinforced elastomeric isolator. First, what we have done, after construction of this up to this level, we placed a wooden plank over here. Over that, we have casted the basement beam at the top of the isolation system, whatever, on the wooden block. Then what we have did, we used jack, and lifted the, this upper beam, and then taken out the wooden plank and replace that wooden plank with your that isolator. So that is how we have done simple, and this we can do in the far-flung area like say Arunachal Pradesh in Tawang. Okay, so that can be implemented anywhere. So our aim is not to develop a system only for so-called engineered and highly sophisticated building, but this can also be used for other simple masonry building also. Okay, so after construction, it looked like this. This is the building. This is a simple guest house, two-story building. These are the discrete isolation system, UFREI. Okay, then we have carried out, vulnerability assessment. I'm not going into detail. We have, for pushover analysis, we have modeled this superstructure. Then this is how, we have defined the, damage states. Okay. So as per this particular paper of Kalbi, published in 1999, and this is the additional, damage state we have defined for the isolator. So this first 4 damage state is for fixed base 1, and last damage state, in addition to this, this is for base isolated 1. So for vulnerability assessment of the fixed base 1, we have carried out numerically for both, of course, and in additional damage state we consider in base isolated building. Okay, so these are the pushover curves. Okay, for fixed base 1, base isolated 1. If we combine these two, here you see this total displacement we have converted to relative displacement, because here with respect to base, so in that case, that is what will be responsible for any damage in the superstructure. So that's why we considered here relative displacement, and then we did uh, 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 develop the fragility curves, and here are the fragility curves for base isolated building. You see fragility, probability of accidents of the particular intensity level will be very, very low. So this also got published in one of the journal published by ASC. Okay, so there's no doubt that vulnerability can be reduced to a large extent. Okay, now next, we have started this work on your partially bonded fiber reinforced elastomeric isolator. There are a lot of apprehension actually. What will happen? During earthquake there will be, because in unbonded case, load transfer basically is taking by friction between your rubber layer at the top and the concrete. So if the reaction, normal reaction changes, what will be this frictional force? Some, apprehension is there. So there are some work done by this Nizad and others, and they have developed this idea, proposed this idea of partially bonded isolators, So here, not entire, zone area is bonded actually. Only core area is bonded, and this annular portion, is unbonded. Okay, and then there will be again a plate at the top and bottom, but as I told you, only core portion will be bonded, not the outside peripheral area. Okay, and then with that, with the help of a pin, we can add another steel plate at the top, bottom and top. Here bottom one is shown, and this one will be connected with your substructure, and top one will be connected with the superstructure. Okay, so more or less, if you see, based on their study only, you see for load displacement characteristic for bonded and partially bonded isolators are more or less same. You see, this is, variation of your lateral stiffness with, increase in the lateral displacement, more or less in both cases same. But you will have some, advantage here, as it mentioned over here, combined advantage of both bonded and unbonded. This type of isolator has a portion of it partially bonded. So, that apprehension will be eliminated to some extent, although we didn't find any problem during experimentation while implementing your unbonded, FREI. Okay. So this is how it looked like, again, based on their work. You see, when in Gilken, they have carried out both for UFREI and FREI, deform shape in both more or less same. Okay, but we'll have additional safety because some amount of bonding is there over here. So that is what we are going to develop in our next step. And this is what we shall employ in the an upcoming building, G+4 building, as I told you, in Itanagar. And here we are proposing to use partially bonded elastomeric isolator in all the peripheral, under all the peripheral columns. Okay, so their variation of your normal direction will be higher, and here column load is also high, and that variation will be low because these are close to your CG of the building. So this blue, dots will be your unbonded FREIs or unbonded fiber reinforced elastomeric isolator. So we will be using both type of isolator combined system in this building for seismic isolation. So there, as because in unbonded and partially bonded, there will be, I mean, difference in height for same properties. So there will be level difference between the two. This is unbonded one in the inside. This is the outside one. As I told, red dots. You know, this red dots. So if you consider a section over here, okay. So here, I mean, bearing height will be a little bit more because of those end plates. So if you consider, say, around, say, 15 or 16 thick plate, so 4 times that, you will have to, additional length will be coming. So that can be adjusted. And for additional safety, you know, we provided a profile at the bottom, something like this, so that there will be, if at all, we have not seen any slip, but if at all uh, 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 that apprehension is there, we want to remove that apprehension also. Okay. So this is the last slide. So far, I mean, India, as has been discussed earlier also, there has been no base isolated building, bridges in India. Possibly this is going to be first base isolated bridge in India. And there will be, I mean, 6, I mean, originally this was planned as an integral bridge, but because of high, I mean, hazard level, you know, designer found it very difficult to design, I mean, piers and foundation. Okay. So now they are changing to base isolated bridge, you know. So there are, for this 6 pylon, you know, there will be 4 bearing in each. So total 24 bearing they will be using in this bridge, which is coming in Guwahati city, third bridge in Guwahati city over the river Brahmaputra, and they will be using friction pendulum bearing. Okay. So I'm not going to discuss this because Professor Matsagar and Professor Jangid will be talking about friction isolation system. So this is just a piece of information. Possibly this will be the first base isolated bridge in India, and that too over a major river. Okay, like mighty river Brahmaputra. With this, I'm concluding. I hope, I mean, I'm more or less in time, maybe 5 minutes more. So
Sure.
please excuse me. Okay. With this, I'm concluding. Thank you for your patient hearing. Okay. If you have any question, I'm here to answer.
Okay, thank you, Professor Dev. That was quite illustrious. We will take up the question after the presentation of Professor Anjan Datta. So now I request Professor Anjan Datta to come over and share his screen. It is also my honor to let our participants know the profile of Professor Anjan Datta, our next speaker. Professor Anjan Datta has obtained his bachelor's degree in civil engineering from Regional Engineering College. Then it was called, now it is called National Institute of Technology from Silchar. He has completed his master's degree in structural engineering from IIT Madras and his PhD degree from the Applied Mechanics Department of IIT Delhi. His area of research interest in the PhD was on adaptive finite element analysis. He has started his teaching profession from NIT Silchar, his alma mater, and then later in 1999 he joined IIT Guwahati. He was head of the department civil engineering from 2006 to 2009, and he has also served as the dean of institute works from 2009 to 2014. He has published large number of papers, more than 100 in international journals and conferences, and guided several PhD students and is the member of many committees. His area of research work are finite element analysis, retrofitting of structures, seismic control, system identification techniques for assessment of damages in structures and others. He is involved in large number of consultancy projects of national importance. So today he will be talking about in the first session, forenoon session on fiber reinforced elastomeric isolation system, particularly with focus on the finite element analysis. So Professor Anjan Datta, kindly take over.
Thank you, Professor Matsagar. You have to give me permission. Okay, got it. Yeah. Okay, at the outset, I must thank ISET and IS Traki for inviting me to deliver this lecture. And this lecture is basically a continuation of what Professor Dev was talking about. So I'll not go to any introduction, and I'll straight away jump into finite element analysis for FREI. Sorry, I have a little problem in my voice because please bear with me. Is it audible, Professor Machaga?
Yes, it is audible.
Okay. So I will also express my gratitude to all my students and colleagues who have contributed to this work. So it is basically the slide which Professor Dev was showing earlier. I am not showing it again. Anyway, now first of all, why finite element analysis for this kind of FREI structures? See, essentially, if you look at all the data which you have in the literature, we have compared the effectiveness of DFREI and UFREI for only model structures and not for a prototype. So obviously, we expected some variations in the behavior. So finite element analysis, when you do, it will give you some more insight. And you cannot actually take the structure, as Professor Dev was already demonstrating, that to a very large displacement level because of constants in experiment. And also you have to use the same isolators for practical implementation. So they may undergo damage if you take them to a very large displacement level, which is typically possible in finite element simulation. And there are also very limited studies with high shape factors. And most importantly, we can clearly see what is the state of stress and strain, and it will tell us what is the debonding level of demand and on the interface between the fiber and the elastomer. Right. So now when you look at FREI, we'll combine both bonded FREI as well as unbonded FREI. Now, essentially there are two components. One is the elastomer, other one is the fiber. Now, elastomer, we have modeled using solid 185, which is the 8-noded element. Now, there are typical two problems in this kind of elements. The two typical locking problems which you encounter are basically called shear locking with the lower order elements and volumetric locking. Now, what is shear locking? Shear locking basically is a function of the geometry, and it occurs because you are using lower order big elements and that cannot bend since they have only linear sides. And volumetric locking will come because of the material, because we are using nearly incompressible material, and it occurs when the effective Poisson ratio is approaches 0.5, because elastomer is highly incompressible. So so that is another area which is what we'll have to address for finite element modeling. Now, what are the ways and means as to how we can get rid of this kind of locking issues? One is you can use incompatible modes, or you can use higher order elements too, but that will only, you can get rid of shear locking. But also you can use uniform reduced integration. See, for example, if I use a 8-noded brick element, I have to use 2 by 2 by 2 Gauss integration. Now, if I use a uniform reduced integration, I can use only single point integration. Now, what will happen? And in that process, I can get rid of both shear locking as well as volumetric locking. But what will happen also in the process, it will bring in what is called hourglass effect, because there will be some zero energy modes, which are actually non-physical spurious modes. So that will create problem in the analyzed results. But you can again get rid of them by using finer mesh. All right. But another way of doing could be you can use selective integration, because that will, but that can only, you can avoid only shear locking. So what we have done, we have used mixed formulation, because when you look at mixed formulation, because why we have used mixed formulation, we can just explain looking at this. See, you have hydrostatic pressure is equal to volumetric strain into bulk modulus. Now, for our case, volumetric strain will be approaching 0 because it is highly incompressible. So your bulk modulus will tend to become infinity. But this is a problem for both higher and lower order elements, because with higher order elements, you can get rid of shear locking, but not volumetric locking. So when dealing with this kind of nearly incompressible material, so what we have done, we have used mixed formulation, because incompressibility of elastomer can result in serious numerical errors if standard isoparametric elements are used, where what you do, you find out stress from the strain. Now your volumetric strain is nearly 0, so finding stress will be actually challenging. So in mixed formulation, you introduce stress also as one of the degrees of freedom. But then there are other problems. Moment you use mixed formulation, the matrix becomes very funny. It will not be like typical matrix what you see, the diagonal dominant, symmetric. Here you may have unsymmetric matrix. Diagonal may not be dominant. In fact, you may have some zero elements along the diagonal. So you have to have a lot of research in the solver itself. So this is what you have to do. But then this is how we have done our analysis. We have used mixed formulation, and we have used appropriate solver like Sparse direct solver, so that you can get rid of this ill conditioning of the matrix. So the element which you have used, solid 185, it has the capability now to model hyperelasticity. We'll talk about what is hyperelasticity all about. And we can also take care of large deflection and large strain problem. Then we have another component which is fiber. Fiber we have taken care of solid 46, which is again a 4-noded layered structural solid element. And it can take care of multiple layers. But here we have used 2 layers, 0 and 90-degree fiber fabric. And so this is how your typical finite element after discretization of an isolator will look like. Now, if it is a bonded isolator, you have a top steel plate and bottom steel plate, and they become integrated, they remain integrated with the isolator. Now, if it is unbonded, the top one will represent superstructure, bottom one will represent substructure, and we'll introduce some contact element in between. So that is what I'll talk about now. So for unbonded, you have to have some contact element. Why contact elements? So you have used, now we have used 2 rigid horizontal plates. They are representing top and bottom, at top and bottom, which will represent superstructure and substructure. And vertical and horizontal loads are applied at the top plate. And so it is allowed to move in both direction, vertical as well as horizontal. And all degrees of freedom of the bottom plate is restrained. All right. Now, what we have done in order to solve this unbonded case, we have used surface-to-surface contact elements. And so the exterior rubber surfaces of top and bottom, that is referred as contact element and represented by quanta 173. And interior surface of top and bottom rigid plates are our target elements and represented by targa 170. And we have used, it actually supports this surface contact elements. It supports Coulomb friction to transfer the shear force. So we have taken a friction coefficient so that there is no slip between the isolator and the top and bottom steel plates. And for bonded FRA, what you have to do is that the contact elements are removed, and you both, because top and bottom plates, they are directly connected to the rubber surfaces. Now, next important thing is the material model, because this is actually you have both elastomer will have both. They have to be modeled both for hyperelastic as well as viscoelastic behavior. Now, let's look at what is hyperelastic behavior. Hyperelastic behavior is basically a type of constitutive model for ideally elastic material for which the stress-strain relationship is derived from strain energy density, that is strain energy per unit volume. So for many materials, linear elastic model which we use do not accurately represent this kind of material because they have, like typical rubber, they have stress-strain relationship are non-linearly elastic, isotropic, incompressible, and generally independent of strain rate. So you have to use something else. So hyperelasticity provides a means of modeling this kind of stress-strain behavior. So we'll see how we can model this hyperelastic behavior. And it is also has got viscoelasticity, which is that it exhibits both viscous as well as elastic behavior. So we have used, there are many material models for representing of this hyperelastic behavior, like Ogden three-term model, Neo-Hooken model, Munley-Rivlin model, and other model like this. But we have used Ogden three-term model, which is quite popularly used. And these are the parameters which we have picked up from the literature. And, and for viscoelastic behavior, we have used Prony viscoelastic shear responses. And these are the parameters which are used. And this is a loading protocol, which Professor Dev has earlier shown also for my same finite element, because I'm comparing my response of finite element model with the prototype, which was tested in the laboratory. And we have taken, for my numerical simulation, we have taken 3 different cases, A1, B1, and B2. And A1 and B1 has got, when you look at shape factors, they're similar, but B2 has got different shape factors. But A1 and B1 has got different G value, and B1 and B2 have got, so that is how we have tested actually 3 different models and 3 different, these 2 sizes are same. This is having a different model size. So like any other finite element analysis, you have to do sensitivity analysis. So you have kept on refining the meshes, and and you have seen what is the response. So we have looked at S33. S33 means that is normal to this plane, the normal stress in the Z direction, And when you look at all the three meshes, you can see they are almost overlapping. So S33 is not much of variation. This is what you are seeing, the normalized stress, S33 by P, that is the pressure which we have imposed from the top. And this is along the normalized width of the isolator. And this we are plotting at the along the width of the elastomer at mid-height level. But when you pick up the fiber, there is some variation. So you have taken the finest mesh size for all our analysis. And this is how it will look like, the deformed configuration, which Professor Dev was showing in the experimental verification. You have a rollover deformation here. This is a half section which we are showing. You have a rollover deformation like this, or there are two ends. And you can see when we carry out finite element analysis and plot both the hysteretic plot, good matching could be seen for B1, B2 specimen, and also for B3. Also for A1, I'm showing some typical pictures only here. And this is a backbone curve, and you can see your experimental data are almost lying over the experimental curve, that numerically obtained curve. Now this is how the bonded one will look like. This is what we have done numerically as well, bonded one and unbonded one, and we have seen what happens to the stress strain state for both bonded and unbonded. And here you can see this entire thing is moving, whereas you have a rollover deformation here. And this is, we have carried out experiment only for unbonded case. So unbonded and up to certain level, up to 0.89 TR, and they are quite nicely matching. And we have extended this to finite element simulation. And you can see the reduction in stiffness is much higher compared to the bonded, obviously. So the transmissibility will be, and so the seismic performance of unbonded isolators are much better than bonded ones. And this is how it looks like. That is what Professor Dev also showed earlier. Now let's look at what happens to the state of stress. So here we are looking at the S33, the stress which is normal to this top plane, and you can see there's a central compression zone and there's a tension zone at two ends. And this is for the bonded one. And similarly, you have a central compression zone and tension zone at two ends. But if you look at the tension value, they are actually much lesser compared to the bonded one. And when you look at the other one, S11, that means in the direction of loading, also again you see there's a compression zone at the center and there's a tension zone at the ends. So essentially they are subjected to bidirectional compression and bidirectional tension. But the magnitude of compression as well as the tension is much lesser in the unbonded case compared to the unbonded one. So compared to the bonded one. So what it means, if the compression is lesser, that means my stability issue will be also improved for unbonded one. And if the tension is also lesser, what will happen? The chances of peeling off will be also reduced in the unbonded case. Now, why this is happening, we'll see. Let's try to understand why this is happening. See, for the unbonded case, for the bonded case, the line of application of the vertical load will not change. It is remaining as it is. All right. So this is the vertical load and this is the reaction. Similarly, this is the applied horizontal displacement, horizontal load, and this is the corresponding reaction. So see, this is forming a clockwise couple. This is also forming a clockwise couple. So you have to have an anti-clockwise couple to balance that for moment equilibrium. And this anti-clockwise moment is creating the tension in this zone. But look at what is happening here. See, because when you have a roll-off here, so when you have a roll-off, just opposite to this, there will be compression. It will try to press against this. Similarly, when you have roll-off at this end, it will try to compress against this end. So what will happen if you have more compression here, more compression there, the vertical load which was there earlier at the center, it will try to shift towards the more compression zone. So it is getting shifted towards the more compression zone. So, and thereby the couple which is generated because of P and the couple which is generated by B will be balancing each other. And thereby you will not require any equilibrating moment. And thereby you have lesser and lesser tension which is developing at the non-compression zone. And that is the advantage we are accruing from this. And if you look at the plot of the normalized stress again for S11, And this is for UFRI and BFRI. You can clearly see the compression. The compression is higher in the bonded case compared to unbonded case as you go on increasing the displacement level. And this is what happens with the corresponding shear strain distribution. For the bonded case, this is uniform throughout the length. And for unbonded case, wherever it is in contact, you have a constant value, but magnitude is similar. And when you compare your different cases with different shape factors, you can see that degradation, because when you look at the effective stiffness, this is for the one case with shape factor 12.5 is this curve, and for the one with 15.5 is this curve. So, and here the reduction rate is about 57%. Here it is slightly lesser. So the specimen with higher shape function, higher shape factor, actually the degradation rate, stiffness degradation rate is lesser. So the most stable. And this is what you can see when I compare B1 and B2. This is what you have with different shape factors. So when you have higher shape factors, you can see also the compression stress which is developing, that is also lesser. For shear, the magnitude is more or less similar, and it is showing the extent of shear will be according to the contact surface. And then we have carried out test, experimentally we have carried out test by applying the load at different angles. And numerically also we have done similar thing. What has been observed that as we go on changing the direction of loading from 0 to 45 degree, the area of contact increases. So if the area of contact increases, and we'll see what is the implication. And these are the results I'm showing for 0 and 45 degree. And so experimental results and numerical simulations are again well compared. And this is what you can see as you go on changing the direction of loading from 0 to 45 degree, the load carrying capacity increases, because you see the shear force is more for the one which is corresponding to 45 degree than the one which is corresponding to 0 degree. And as I said earlier, the support, the contact area of the isolator with support surface increases as the loading direction changes from 0 to 45 degree. So at a large horizontal displacement, some parts, so what will happen? As you go on increasing the displacement, as you can see, it is rolling off, rolling off, rolling off. At some point in time, it will come in contact, it will come and rest with the, will be in contact with the support surface. So when it will come in contact with the support surface, let's see what happens. This is what will happen. See, up to about U, which is up to about 0.2 R, 0.2 TR, you will find between 0 degree and 45 degree, there is not much variation. They are all overlapping. Now, when you look at the range from 0.2 R TR to 1.7 TR, you will find that 45 degree, the one with 45 degree direction of loading is having showing more load carrying capacity. Now, if you go beyond this, you will find now there is a stiffening regime coming in. And this stiffening, you can see now, this is happening at a earliest displacement which you see, that is happening for 0 degree. The same stiffening you will also encounter when you go for different direction of angle, load angle of loading, but they come much later. So that is what we have observed. The displacement limit corresponding to hardening behavior, but there is a hardening. There will be hardening for any loading direction, but the displacement limit corresponding to hardening behavior is observed to increase as the loading direction changes from 0 to 45 degree. And you also see the variations of effective horizontal stiffness with horizontal displacement in different direction. And you can see that effective stiffness, this is corresponding to 0 degree. Effective stiffness is more for 45 degree angle of loading than 0 degree of angle of loading, but damping is reversed. You have more damping corresponding to 0 degree than 45 degree. And when you look at again a similar stress plot, you can see again this is of course for 0 loading, which you, and for large, much larger displacement, and this is for 45 degree loading. And when you look at this plot of normalized stress again, you can see that the one corresponding to 0 degree, 45 degree shows your stress level is higher compared to 0 degree of loading, 0 degree loading case. And but strain, it is reversed for shear strain. Now, but this is what you have seen for unbonded case. But if you change the angle of loading for bonded case, you can see both the curves actually overlapping. There is no change. But for unbonded case, when it is for 0 degree, for 45 degree, for 0 degree, it is like this. But for bonded, both are actually overlapping. So these are some of the conclusions which we can draw. Good agreements observed between the findings from experimental and finite element results. Horizontal stiffness of UFRI is significantly lesser than BFREI, and hence possess significantly higher seismic isolations efficacy. Significantly lower compression stress demand in elastomer, as well as lower peeling stress demand in bonded case compared to unbonded case. And peak values of compression stress in elastomer, UFRI is smaller, with smaller shape factors, are higher than those with higher shape factors. And loading direction changes from 0 to 40, you see K effective, it increases in the given horizontal displacement up to, and then there is some variations beyond 1.7 TR. Now, we understand that there is a nonlinear load deformation characteristic for unbonded case. So because eventually you'll be testing it, but then you initially have to have some design guidelines so that you can come up with the sizes, and then you can manufacture before you actually test it. So we have to have some guidelines for initial design, and we have looked at the literature, and we have found that it is all there for SREI, and then there are some recommendation for FREI also. And but there are some discrepancies, which is what has motivated us to improve these recommendations. So this is what is available for SREI, and we have recommended for bonded FREI something like this, because we understand that A is not going to change, but if at all there is a change, it will be in G effective. All right, and we have looked at the literature, and we have found for bonded FREI, Gerhard group has given some suggestion like this for G effective, for bonded, and for unbonded case also something like this. All right, and but also we have seen there is another recommendation by Nezat group for K effective for unbonded, where they have not done anything for G, but they have played with A effective. So what we have done, we have combined both of these, and we have tried to see how they match with the experimental as well as finite element simulated results. This is what Professor Davis talked about A effective, so I'm not going to that. So we have, if you look for the bonded case, we have only played with the G effective, and this is what we have plotted for different values of G. We have seen how they vary with displacement level. And so this is, we have proposed two methods, one for method one, where we have not really bothered to see what is the influence of the displacement limit. And in other case, we have seen, okay, we have proposed two different expressions for two different displacement ranges. And then when we have plotted for unbonded case first, you see this is what you can see for the existing one, Gerhard and Nezat. They are, and this is my finite element results. Okay, finite element result is this pink line. So they are nowhere close to that. And we cannot doubt our finite element result now, because my finite element result is also matching with my experimental values. All right. So when you see our proposed method one is actually this, and proposed method two is this. So we could see proposed method two is very nicely matching with this. Similarly for other shape factor side, B2, and this is for A1, this is for B1. But however, for B2, we have seen proposed method one is relatively better than proposed method two. And so also we have seen for bonded case. So we can understand that we have some expression now in place, and this can be used at least for the preliminary design for bonded as well as unbonded FREI cases. And then you manufacture them, get them tested, and see how they perform. So this is, again, I'm not reading the conclusion. This is what I've already discussed. Now, having done this numerical exercise for bonded and unbonded case in terms of evaluations of their horizontal characteristics, load displacement characteristics, we also should know how good are they in terms of the stability, vertical stability. So if we have looked at the literature, we found that there are some suggested models, but most of them are for bonded case. And even if there are some cases, these are for UFREI, they are for scale models. So we thought we should do it for a prototype unbonded case. So what we have done, we understand that the critical load capacity of the elastomeric isolator can be defined as the vertical load for the horizontal stiffness is reduced to 0. This is a standard definition. But in addition to the vertical load, we also have horizontal load. So we've looked at what is the horizontal load displacement curve, something like this. And the point of maximum shear force is considered the stability limit defined by the critical horizontal displacement UCR corresponding to vertical load referred to here as the peak CR. So this is how we have defined as PCR. So we can write KH as dF by del U equal to 0. And we can use chain rule. And here we can get rid of this. We can play with, we can assume that, okay, if my dP by del P by del U is 0, what will happen? And eventually that will be 0. So this is what we are looking at. So we'll play with this del P by del U. Now we have got this kind of history plot. So we have looked at this again based on the recommendation from Tupoch and Nezat. We have looked at a curve, fitted curve, which passes through the central line. So that means we are not taking care of the effect of damping. So we know that the total horizontal force will be a combination of the stiffness force and the viscous force. And the stiffness can be, the stiffness force can be modeled using a fifth order polynomial, something like this. And then we find out what is the derivative of this. All right. And then there is another recommendation we could see from Stanton, who defined the tangential stiffness at 0 horizontal stiffness, horizontal displacement as the, so this is what we are calculating as tangential stiffness. Now he's saying tangential stiffness at 0 horizontal displacement will be termed as transverse stiffness. And we'll find out what is the vertical load corresponding to 0 transverse stiffness, and that is what will give us the critical buckling load. So this is what we have done. And this is the loading protocol. We have gone on changing the vertical load from 350 to 850 kilonewton gradually, and loading horizontal displacement from 80 to 135, because up to 80 there is nothing going to happen. And these are your different historetic plot, and we have found out what is the corresponding fitted curve for different variations of loading as well as displacement amplitude. From this fitted curve, we have found out what is the plot of tangential stiffness versus horizontal displacement. And from here, you find out what is the corresponding horizontal tangential stiffness at 0 displacement level for different loading, different displacement ranges. And this is what we have plotted. So you get, for corresponding to 0 horizontal displacement, you get the transverse stiffness. So you plot vertical load versus transverse stiffness. And wherever you have transverse stiffness 0, that will give you the buckling load. So this is what finally we plot. So for our specimen, we could see the buckling load is far, far higher. So your specimen is safe. And that is what we have seen when we have actually implemented them. We could see any bulging whatsoever. So they're absolutely fine. So, and we could also see what is the variations of effective stiffness with vertical load. And you can see that it actually decreases with increasing load, whereas damping increases with increasing load, increasing horizontal displacement. So these are some of the conclusions. And this is the typical building which Professor Dev shown earlier. I'll just show you that how we have modeled the entire building system. This is a building. And we have done actually modeling of these structures using both SAP as well as Abacus. In SAP, we have used a nonlinear layered shell element. And these isolators we have designed, we have modeled using rubber isolator elements. In fact, this is a Bokman model only. And we have used a bilinear hysteretic model. We have taken equivalent bilinear hysteretic characteristics. And we have used a molecular model here because SAP doesn't have any other model. But for in Abacus, we have used a CDP model also, and we have compared the performance. They are coming similar, more or less similar. So using this molecular model, obviously you have to use the stress strain behavior both in compression tension and the shear stress versus shear strain behavior. And we have seen this kind of characteristic. We have used ground motion as Kaina, and you can see the performance between the fixed base building and base accelerated building. Your base accelerated building is showing huge amount of reduction in acceleration, and whereas base accelerated building is this is at roof level and this is at first floor level. So you can see huge reduction, and this is for interstory drift. You can see interstory drift is much lesser, and horizontal displacement is what you can see. We have to ensure that horizontal displacement, whatever we have designed our isolator for, the horizontal displacements are well within the limit. So this is what you have ensured. So from floor accelerations and interstory drift, we can see that base accelerated building acceleration from earthquake are significantly lesser than those of fixed base building. And UFRAs maintain stable rollover configurations within the estimated displacement limit. UFRA is found to be very effective in reductions of seismic vulnerability of low-rise masonry building. Thank you. I think I have finished within 1 o'clock.
Okay, thank you, Professor Datta. So it was very nice that you have met the time requirement as well while presenting all the details in the finite element analysis. I request Professor S.K. Dev also to now again switch on his video. Yeah, and there are several questions which are already put in there. So I will take up one by one, and before doing that, I request the audience again to type in their questions either in the question answer box or in the chat box, wherever. So I'm taking the first question. It is asked by Professor Mahesh Tandon. He's asking, what is the design life of these bearings used for buildings and those shown for the bridge?
Design life of the bearing, what they are supposed to use in bridge, the designer has mentioned it is 100 years. Okay, this is a friction pendulum system, and as far as fiber reinforced elastomeric bearing is concerned, these are basically, I mean, material is elastomer and your fiber. Fiber, you know, is a highly durable material. Elastomer is also well tested. So in that sense, I can safely say elastomer anyway, conventional bearing are in use in India or elsewhere for a long time. So it will be obviously, I mean, more than around say 50 years, 60 years.
Okay, I would just extend this discussion, Professor Dev, ahead. If you have natural rubber and if you have synthetic rubber, then that would have some effect on the edge. Kindly comment on that.
Yeah, so far whatever we have studied in our case, we have used, I mean, elastomer. Now we are going for, I mean, now our there is a request from one of our contact in Canada. They want us to test with natural rubber. So we are going for natural rubber. As of now, we have not done any testing on natural rubber. Now we are going for natural rubber also, because that will be cost effective. Because in India, particularly in northeastern region, a lot of rubbers are available in Tripura and all. In Kerala, anyway, is a rubber source. So, but then what will be the impact of on damping and durability? That we'll have to explore. At this moment, I cannot comment. But then Professor Kelly and others, you know, they have used natural rubber for high damping bearing also. So definitely, I mean, there is a scope for utilization of that as well.
Yeah. Thank you. Another question, there are actually two questions, is from the next session panelist, Mr. Vipul Mehta. So his first question is, please comment on the minimum stiffness requirement for the purpose of recentering the structure post-earthquake, and how much effectiveness of the isolation is compromised on this count.
Last part, I could not hear. Last part.
Yeah, how much effectiveness of the isolation is compromised for the sake of recentering?
Now, as far as elastomeric bearings are concerned, or multi-layer, whether high damping or lead rubber and all, recentering, because these are all, as you all know, I mean, all of us know, these are non-linear elastic material. So as the Professor Datta has already indicated, you know, as long as your effective stiffness is positive, you know, there should not be any problem in recentering. And anyway, we are testing as per ACI code or any other code, you know, whatever seismic weight we are supposed to apply in vertical direction, that we apply, plus whatever maximum displacement we impose simultaneously, you know. So, and as per ACI 7, you will have to test the bearing. So experimentally we ensure, and theoretically, as Professor Datta has already mentioned, those theoretical aspect, you know, of critical load determination. From there also it is clear, as soon as your effective stiffness on positive side, you know, yeah, there should not be any problem as far as that recentering problem. Maybe the earlier used to be there with plain friction bearing and all this stuff. So there will be slip. Here there is no slip actually. Even for unbonded also there is no slip. It is always in contact. It is losing contact in certain zones, what we call it rollover. But as such, you know, there is no relative displacement between bearing top or bottom with the superstructure or substructure. And it's because it is linear elastic material, non-linear elastic material. So I
Actually,
don't see
there is sometimes there is a problem for the whole building to come back to the center where it was. It's regardless of whether it was, unbonded or bonded. It's a problem even with, friction pendulum. As far as,
friction pendulum is your friction pendulum is a sliding bearing. But
right. So even, we have that problem. If you provide too less stiffness, then this problem will occur anyway. So this is what
So in that case, please complete. Then I shall respond.
Yeah. So basically, it's it's a double-edged sword. On one hand, it's good that you have a longer, or lesser stiffness so that you get more isolation. But more, you have to provide more stiffness so the building comes back. All the services, everything will be disturbed otherwise.
No, actually, this problem in sliding system.
This thing is already there in ASC 7. There's a requirement over there, 2.5 times the weight of the building is a restoring force at some 50% maximum displacement or something like that is there. So you have to have a minimum stiffness like that for that to happen. I mean, we don't have anything in our code as yet, but this is a very important part which I think should be highlighted with this particular material.
Yeah, what you are talking. What I told, it is related to, laminated rubber bearing, whether it is steel reinforced or fiber reinforced.
Either way, this is important.
There is no issue. Issue is, as you said rightly, sliding system. But if you look at the genesis of friction pendulum, earlier people used to say truss system. One system was there, where friction interface was stainless steel and PTFE. And in that laminated rubber bearing, they used to use for recentering. So that kind of system was earlier there. Then Professor Mahin and his group in Berkeley came out with this friction pendulum, and by curvature they ensured that recentering is there. So and in any case we are testing, as per all the codal requirement, whatever is the design vertical load you will have to apply, and also you will have to impose the horizontal displacement. What do you anticipate, or what is prescribed maximum displacement prescribed by the code. So experimentally also we are ensuring that there is recentering. That's how I can answer. That is what
Yeah, he is also asking Mr. Vipul Ahuja regarding the aging of these isolation system, particularly with respect to the kind of rubber being used.
Rubber bearing, already I told you, as far as elastomer is in use for quite long time, and around 50, 60 years, 50 years, say, plus minus 5 years or so.
Okay.
And as far as sliding, your bearing like your FPS or FPB, whatever you call it, they are claiming it is 100 years. Generally, these sliding bearings, main issue is your generation of high frequency component. Okay, that's why they are reducing the friction coefficient at the interface. That problem is not there in this thing, but then there is a limitation on your high load in elastomeric or laminated rubber bearing, whatever you call it, natural rubber or elastomer. So that bridge, what I shown, the bearing load will be around 4,300 ton. That is what for that. Of course, I have to check entire design. Just I got that assignment. I'm asking for all the this thing information from the designer.
Yeah.
So let's see.
Okay. Next, there are a couple of questions. So I will take a few of them from Dr. Mohan of BITS Pilani, Hyderabad. So he is first asking, is there no other simple way to place the isolator without jacks?
Jack is the simplest thing. What we used in Tawang, it is the remotest part, a truck jack we used. No specialized jack. Okay. So multiple jack we used. Say 3 side we use jack, and the open side we replace that wooden log and place. That is the simplest of all. Okay, so we use there. That is a very remote area. All of us know, and there. Without taking any help of any external agency, they could manage. This PWD people could manage. Okay, using simple track jack. Okay, of course they placed one plate above and one plate before for, I mean, dispersion of the load. But then, and we cleared it by say a millimeter or two. Just when it is free, we are taking out. We are not lifting by much.
And then he's asking what are the main challenges now for the these kind of isolation systems, and particularly how can it be made adaptable in mass scale for low cost earthquake resistance in our country?
Now, yeah, that is, I mean, that industry butter already I have shown they are manufacturing this. And patent we have applied long back, it is due. I mean, so, I mean, they will be able to supply. And as they are supplying for that proposed building, you know, which is already planned, and we ordered that. And as I told you, one has to have the testing facility, because all the codes need, I mean, testing facility. So for building, I don't think column load will be a normal building as a G+4 or G+5, that kind of building, you know, no column will be having more than 300 ton. So keeping that in view, we have this thing. But for bridge, you know, we need, I mean, huge testing facility, or of their order of, say, Encre, I have seen they have a test facility F-frame for 3,000 ton or 30,000 kilonewton. Okay, but that is not enough for that bearing for the, I do not know. I'll have to ask this question to this designer where they are going to test. Okay, even in ELSA lab, I mean, they have, I mean, very good, I mean, facility for testing, but I'm not sure whether they have more than 3,000 or 4,000. But then they claim that they have used this bearing in one bridge in Turkey, Asin Bridge. So Ajin Bridge. That is also some kind of cable stayed bridge. So there they used. So I'll have to ask all the queries regarding this. So far they have not furnished any test result. Okay, so obviously without test result we are not going to permit.
All right, sir. Next question is for Professor Anjan Datta. The person who has asked this question did not mention her or his name. So it is asking which software is used to assess the nonlinear behavior of the FREI bearings.
ANSYS, we have used ANSYS.
Yeah, and how to ensure the properties of isolators in all the directions it is same, and how the orientation of fibers is decided. It is asked by Sarvesh Kumar Jain.
Yes, when I have used this fiber element, there is a provision for properties along different layers. So since we have used at each layer, we have used only bidirectional fabric, we have given the 0-90 degree properties. So you have to give your properties accordingly, 0-90 fibers. So this is for your elastomer. And for this is for your fiber. Elastomer is isotropic. So basically, whatever hyperelastic properties and viscoelastic properties, that is true for all the directions. So it is independent of the directions. Yeah.
Okay. Thank you, sir. Next related question to this is currently in this work, the rectangular or square shape isolators have been used. What is your opinion about if we are using circular shape isolators? Will they be perform better or worse? Asked by Mr. Raman Boli.
So there are studies in literature also using circle. So I mean, it is up to your convenience. It actually does not show you anything any specific advantage or disadvantage either.
There is another question on the performance in deterioration because of the repetitive earthquakes. So is there any way to account for it? Asked by Saiteja Sistana.
Professor Dev, you can.
As I already told you, material is non-linear elastic. So if there is no damage, so there should not be problem in repeated, use.
And we have actually done repeated testing for many isolators, and we have found the performances similar actually, even in a lab scale.
Okay, there is one question from Mr. Dheeraj Ahiwale. Which type of base isolation system could be effective for long span industrial steel truss frame subjected to vertical ground motions?
Vertical, generally we isolate for horizontal this thing normally. Vertical isolation, that means you will have to incorporate vertical flexibility also. So, I mean, it is a specific answer will be difficult. What is the structure? What is the period and all? And then same concept we'll have to extend. There are three-dimensional isolator also. Particularly nuclear power plant, they also look into this issue of vertical acceleration isolation. Okay, so it is possible. It is designed here. As because building, very stiff in this. Traditionally, we don't go for vertical isolation, but then we ensure that rocking is prevented by providing very high stiffness. Otherwise, we don't go for vertical isolation in vertical directions. Okay, so as we all know, vertically, I mean, more or less, building don't suffer any problem, because problem is your horizontal components. So yeah, it is possible. There are isolation. In that case, you'll have to tune the stiffness in the vertical direction also, and you'll have to satisfy both criteria. Like horizontal direction, what you do, same thing. You'll have to extrapolate in the vertical direction also, so that you get isolation at the same time. Stability is also not sacrificed.
Okay, so next question is, I think it is from Dr. Ajay Chaurasia of CBRI. So he's asking, how would be the behavior of ballastic fiber instead of GFRP or CFRP?
Ballastic fiber, I do not know what is actually. It depends. Actually, durability should dictate. Otherwise, if durability and E value should be very high, because you see, if our carbon fiber E value is much higher compared to steel. So, I mean, that's how, I mean, you'll have to decide. If E value is high, durability is there, then they can use other fiber also. So these are the two parameters that is coming in my mind at this point of time. We'll have to see E value. If it is, I mean, it's okay.
Okay. There are a couple of questions asked by some of the participants. I'm just putting them together because most of them are related to the cost effectiveness of the isolation system, asked by Harshdeep or Sukalyan Sarkar. So they are asking, the fiber reinforcement might be a costly material, and therefore if we compare with the conventional isolation system and these isolation system, how do they compare on the cost part?
It is, I say, for the building, for what we are contemplating at this thing, Itanagar, that is a quite, I mean, relatively larger building, I know, medium-rise building, you can say, G plus 4-story building. So there we have estimated roughly, I mean, entire building cost will be around, say, 10 to 12 crores, something like that. Exact figure I do not know because I didn't see the estimate. Roughly. And total isolator cost will be around 65 lakhs or so. So around, if you calculate, it will be something between, say, 5 to 10% or 6-7%, something like that. So whatever information I have, any isolation system, if it is around that, then it is acceptable. So additional, but unfortunately, I mean, all the codes, I am not blaming any particular code. As you know, reduction factor for superstructure is 2, it is reduced. So that's why we could not offset the additional cost of the isolator from savings in the superstructure, because codes are not permitting that. So if a time will come, probably code will permit, and economy of scale also will come into the picture. That point of time, I think, I mean, cost will come down for all types of isolator, and we shall be able to.
No, but I'll just add, but compared to SREI, FREI is much cheaper, much cheaper. Because somebody was pointing out that carbon fibers are expensive than steel. No, your weight, manufacturing cost, top and bottom steel plate, there, everything put together, your SREI will be much expensive than FREI of comparable size.
Comparable loading capacity. Size will be smaller for loading capacity.
There are some questions related to the type of building in terms of its irregular plan size, or whether the contact that gets loosened, it will have effect on the performance, and how to account for it in the modeling. So some of these questions are asked by different participants like Mohammad Aratsu and then Ravindra Golia, that if there is some loss of contact particularly in the unbonded bearings, then the area of transferring the vertical load reduces. So how does that affect the overall design of the bearing and performance?
That is what we discussed throughout our lecture. In spite of losing this contact area of contact, even if it is bonded, as Professor Datta has told, the red region, that anyway is not helping us, no? So that way it gives a sense of security, I mean, psychologically you can say, but in this obtuse corners, in bonded case, there will be always high tension. Okay, so it is no way, I mean, helping us. So that's why, in spite of reduction, we didn't see any, inferior performance.
Central compression core is more or less
same in both cases. Compression core, which transfers the particle load, more or less same in both cases.
Okay.
And another, what you wanted to know, first part is this. Anything else?
Yeah, the irregular buildings, if there are
irregular building, yeah, we can arrange the, basically irregular building, CM and CR, are having offset. So by appropriate placing of the bearing, by selecting bearing of appropriate site, appropriate location, we can reduce that E, isn't it? That's how we can, mitigate the problem of eccentricity by selecting appropriate size of bearing and different locations. So that, CM and CR come very close to each other. That's it. And then torsional coupling will not be there. Or even if it is there, it will be very, very minimal. Okay, you cannot make zero. So there will be some, minimal eccentricity will be there, but that we can be nullified by placing right size bearing at right place, so that CM and CR come close. So it is possible to, mitigate problem of plan asymmetry and other things, by base isolation system.
Okay, there are still several questions left, but because of time constraints, I will take the one which is the last question. However, this question is little off the topic, but still quite relevant to the discussion that we have had today. So I would request both Professor Dev and Professor Datta to reply on this. So the question reads, and I will read it verbatim. The earlier release of IS 1893 in the year 1984, showing zone 1, which was revised and pushed to next higher seismic zone 2 in the IS 1893-2002 revision within a span of 18 years. Can we expect some modification in the seismic zones in near future? Also, it is to be noted that our infrastructure projects, we are designing for 100 years of design life. So are they safe in the current seismic codes, and are we required to redesign them for the higher zones to cater for the changes in the codes in future and make our structures safe?
We design any structure according to current state of practice. We cannot wait for, future development for design. So if we see, in future there is a, upgradation of code or, more, knowledge we are generating, to take, and if at all, that poses higher seismic risk, then we'll have to go for retrofitting. So that is, that is what I can say. We cannot wait for, future studies or future mitigation measures, and we cannot say, we'll have to create our infrastructure. No? So always we do that. We design all our structure as per our current state of practice. Earlier we used to design by, say, working stress method, then ultimate, then your limit state, so things are progressing, so we'll have to move accordingly, and if we find a structure is deficient as per current code, there is no other option. You will have to upgrade if you want to ensure safety, retrofit.
Okay, Professor Datta, your comments, please.
Yeah, I think, retrofitting is only key if your structure demands for the functionality to be continuing in a manner it is now. And if it shows some seismic vulnerability, obviously you have to do the retrofitting. So you have to, now there are ways and means of finding out the weaknesses. We know that you can carry out performance-based analysis, find out the specific weakness and find out where exactly the retrofitting is needed.
Okay.
With
Thank
permission
you for.
of Professor Masagar, if I have a
Yes,
minute,
please.
just one little thing. The whole
Yes, sir, please.
fries, I call them. They remind me of in Japan. I think we were told by Professor Akira Wada when he was there also, and I think there was some comment on this. There was a treasury, a king's treasury, which was constructed hundreds of years ago, and the concept was very similar in the sense that there were a whole bunch of round timber columns on which this building was resting, and to date it is there. So whenever there's an earthquake, the whole building it doesn't slide, but the columns rock and then recenter again because of the self weight. Okay. So just by intuitive this thing, the whole system was working, and it stood the test of time. So I think there is good promise in your unbonded FREIs. It's a very intuitive concept also, from which has withstood the test of time. I just wanted to add that in as
Yeah. Thank you, Saab. Bhaumik Saab, would you like to give some closing comment before I put the vote?
Yeah. Thank you, Professor Matsagar and all the Professor Anjan Datta and Professor Sajal Dev. I think it was a fascinating lecture. I just wanted to comment on the last question, which was very ably answered also by both the professors. See, codes are continuously changing, and as very rightly pointed out by Professor Dev, that we have to design based on the current state of practice, and as and when the codes improve, we have to do the retrofitting. But the beauty of the base isolation is that we are decoupling the seismic energy in the building, and therefore the whatever changes in the seismic zoning or the basic loading comes, the least affected will be those structures probably which are base isolated. I mean, the
Yeah.
sensitivity of the building to changes in the code will be minimal. So that is
Minimal,
the point
right.
which I wanted to strike upon.
Excellent,
And
excellent. That is what I
I
wanted
think
to say.
yeah. So before I hand over to Professor Matsagar, I want to profusely thank Professor Matsagar for very ably conducting and moderating this particular session. And to all participants, my request is kindly join back at 3 p.m. for the second part of this webinar, which will be on the sliding mechanism of base isolation. We have two parts. The first part very ably conducted in the first session. The second part will be on the sliding mechanism, and I look forward to all the participants joining in there. Thank you.
Thank you very much. Yeah.
Thank you.
So thank you, everyone. And
Thank you, Moshik.
we look forward to joining you once again at 3 o'clock today.